Hey everybody, pause the video and go grab your calculator. We're going to spend a minute and a half working on calculator skills. And now that you're back and you've got your calculator, let's get started. Okay, so let's press beef graph when we're on the home screen and tab to enter the function in. Let's go x raised to the third power, exit the exponent, minus 10x. Yikes, can't even see the top of this curve. All right, menu, 4-window zoom. I think I want to choose 4 zoom out. Where's the center? Click, 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 click. There's the center. Now we can see the relative min-max. Menu, 4-window zoom. Let's do a zoom box. Click, drag. And now the box that I had is the window. Menu, 4-window zoom. Let's do zoom fit. This is the computer's or the calculator's best guess for what you want to see. Tab. Let's clean things up. Up, control, delete. Don't delete the equal sign. Enter. And let's put the zoom back, the window back the way it was. 4-window zoom, 5 zoom standard. And now it's kind of familiar the way it was. On to get back to the home screen. That's it. Hey everybody, welcome to section 1.3, Extrema and End Behavior. So this is what your package should look like, and I'd like you to actually copy some examples from Desmos. So it'll look like this. Maximum. Here, let me show you what the maximum looks like. You can say verbally, we often say in a sentence, that the function has a maximum of 11.5. What that means is it's the highest point on the graph, and it's the greatest value in the table. The function has a maximum of 11.5 at x equals 12. Let's focus in on just from 0 to 22 or so. We can see that that's the highest value. And in this particular window, we can say that the function also has a minimum of 1.8. 1.8 is the lowest value you're going to get to on the graph, and over here we can see that this output is lower than all the others. And where is it exactly? It's where x is equal to 4. When x is 4, you get your minimum of 1.8. There's also something called a relative maximum and relative minimum. So a relative maximum is here. This has 3 relative maxima located at x equals 0, x equals 12, and x equals 16. You can see in this kind of small little neighborhood, the highest point is going to be here at 2.8. And in this tiny little neighborhood, not the whole thing, but if you zoom in enough, you can convince yourself. I wonder if I could zoom in right now. Probably not. Yeah. As if you zoom in this little green dot, if you were only looking at just this tiny little green dot area, you would think that the highest point of the little green dot area is this, x equals 12. And then here, x equals 16, you get another maximum of 10.2. Here's a relative minimum. You can see there are 2 relative minimum here, one at x equals 4 and another one at x equals 14. Again, if you were to zoom in, disregarding the other spots right here or the other spots over here, if you zoom in far enough and kind of blind yourself to everything else that might be around, you could convince yourself that it's just the lowest point right here. That's what relative minimum are. And if we're just looking from these, since we don't really know what happens after 24 hours, we have to restrict our discussion of this function to the interval 0, 24. That's what we might call a restricted interval. Again, the flight of a drone. Let's say the maximum would be this. You can see the highest point that we can see here is the function has a maximum of 230 feet when x is equal to 7 minutes. 7 is the x value, and the actual maximum is 230. It's the highest number on the table. The lowest number on the table is 0. This function this function actually starts here, doesn't continue down into negative space. So we can say that it has a minimum of 0 feet when x is equal to 0 minutes. A relative maximum is right here. If you kind of zoom in and restrict the interval, restrict your field of vision to only this green dot area, it might look like this is a maximum. So we call that a relative maximum. The function has two relative maxima. It's got one at x equals 2 and the other one at x equals 7. And you can see kind of surrounding it, if you blind yourself to all other parts, this 120 is bigger than 0 and bigger than 60. Same thing here. If you kind of restrict your vision to just a small neighborhood around this, you could convince yourself that this is a relative maximum. Relative minima. So you can see here, if you restrict your vision to just this small orange dot, you could convince yourself that the smallest point is, the smallest y value is 0. So it has three relative minima. One at x equals 0, one at x equals 4, and the other one is x equals 9. And what are the actual values? 0, 60, and 125. Let's go back to the notes. So what exactly is a maximum? Maximum is the greatest output value of a function. Sometimes they have a maximum and sometimes they don't. But if they do, if they have one single greatest output value, that's what the maximum is. You need to make sure your window is zoomed out enough so that you're not looking at kind of a narrow area. And yeah, I just wanted to say that. And then also, the maximum is also called in other textbooks a maximum of a function or a global maximum, but that's what we call it. And very much in the same vein, a minimum is the least output value of a function. And again, the same note applies. You've got to make sure that your window is zoomed out enough. If you got tunnel vision and you're only looking at a very small area of the graph, then you might not actually identify the minimum. You've got to zoom out and convince yourself that zooming out further isn't going to give you any more information. So this is also called the minimum of a function. It's also called a global minimum. Relative maximum is the greatest output value of a small zoomed-in part of the function. And a relative minimum is the least output value of a small zoomed-in part of the function. And this is only, if you zoom yourself in, you're not considering the borders, you're consuming only the center part. You're looking for an open interval. And I think I can talk more about that tomorrow if you like. So Extrema, and you notice that's what this is, a collection of all these things. Extrema is a collection of all the relative or global minimums or maximums. Like if you have any of these, put them all in the same container and the name of that container is the Extrema. Like a maximum is a special kind of Extrema and a relative minimum is a special kind of Extrema. As you see me doing, these have often been identified by the x values. So, for example, you could say a social media post function has a relative minimum of 900,000 posts at x equals 14 hours since midnight. We identify it by the x values. The flight of a drone has a relative maximum of 120 feet. That's the y value, that's the output, and that is the maximum. Where is it? Is it at x equals 2 minutes. The prepositions we usually use are of and then the y value, like of 120, of 9, and then at the x value, at x equals 2, at x equals 14. That's Extrema. We can talk more about it when we get to class. There's a big question also in this, like this section talks about two things, Extrema and End Behavior. And End Behavior goes towards basically asking the question, what happens to a graph after it leaves the window? Now, assuming that the window is zoomed out enough that we can assume that there are no more changes in direction. So take a look at this graph. Really fascinating graph. You can imagine if you were zoomed in too far. Can I zoom in right now? If you restricted your scope to only looking at this part, you might miss out on all the other stuff that's going on. Or if you had been zoomed in so much you're only looking at this, then you miss out on all the other stuff. So you have to really make sure you're zoomed out enough to begin answering questions like this, like Extrema and what happens to a graph after it leaves the window. There are four very common kinds of end behavior. So here's the window, and sometimes the graph will just continue up forever in this direction, in the negative x direction, and continue up in as well to positive infinity in the positive x direction. So we call that up end behavior. How's it going to end? Up and up. And similarly, this is down end behavior. This is down up end behavior, and this is up down end behavior. Let me show you what I mean. Over here, this has got this curve right here of the graph of this graph is has down up end behavior. If you zoom out further, you're not really going to change what happens to this graph as you look further left and left and left. It's just going to keep on going down, 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 down. Similarly, if you keep on looking right over here, this is going to keep on going up, 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 up. So we call that down up end behavior for short. Now, each one of these arms, the left arm and the right arm, left arm, right arm of the curve that go either to positive or negative infinity, can be spoken about individually. So let's just take a look at this one right here. We can say, quote, as x approaches, in this case, positive infinity, as the curve goes to the right and keeps on going to the right to positive infinity, the y value will approach positive infinity. So just describing this part right here, that's how we'd say it. As x approaches positive infinity, y approaches positive infinity. Down here, we could say as x approaches negative infinity, going to the left, you say the y values approach negative infinity as well, meaning you can go far down as far down as you want by simply making sure you go far to the left as you want. That's what that means. So that's all the new stuff. What I did want to recap some of the things we already also learned. We learned about intercepts. We learned about even algebraic tests for even or odd. On domain and range, I wanted to also ask those questions about this curve. So, for example, what is the y-intercept? Well, here's the y-axis, and it intercepts right here. So the y-intercept is equal to 0, as indicated by this point, 0, 0. The x-intercept, it has, count them, 1, 2, 3, 4, 5 x-intercepts. It has an x-intercept right here at -2. It has an x-intercept right here at -1. It has another x-intercept at 0. It has another x-intercept at 1. And I want you to tell me what the last x-intercept is for your red dot question. It also has a relative maximum of 3.631. Here, relative maximum. If you could zoom in on this part, then it would look like it was the overall maximum of the function. That is, and it has an x value of -1.64. So the relative maximum is 3.631 at x equals -1.644. There's another relative max, same thing right here. The relative maximum is 1.419 at x equals 0.544. And you could do the same thing for relative minimums. Here's another relative minimum, here's another relative minimum. And the numbers are right here. It actually has no absolute global minimum. It doesn't have a global maximum because it doesn't matter what, because if you zoom out far enough, eventually you'll see that that this keeps on going to infinity. If you tried to say, this graph will never go above 100, well, just trace it far enough and eventually you'll get above 100. So it has no maximum. You could try to say, oh, it has a minimum value of -500. Well, just go far enough down and eventually you'll get past -500. So there is no minimum and no global maximum. Let's do a little bit of algebraic tests for even or odd. This is the actual function. This right here is the curve x to the 5th minus 5x to the 3rd plus 4x. So let's do the even test. We've got the function. We have to figure out what f of -x is. We put -x in each time we see x here. So it's x to the 5th becomes parentheses -x to the 5th minus 5 parentheses -x to the 3rd plus 4 times parentheses -x. we simplify them, and if you take this negative x times itself 5 times, it's still going to be negative x. And negative x times itself 3 times is going to be negative x to the third. It'll cancel out with a subtraction, and that's why this is positive. And again, 4 times negative x becomes negative 4x, and you can make that subtraction. So that's what f of x is, that, and f of negative x simplified is this. And compare the two, and they are not the same. They're not equal, so that fails the even test. Let's do the odd test. Notice we've already got the first half of the odd test right here, negative x to the fifth plus 5x to the third minus 4x. And we have to compare these two. We have to compare f of negative x to negative f of x. Let's see, negative f of x would be negative, and then the entire f of x gets substituted in here. That's what this is. If you make the whole thing negative, you change all the signs of all of the terms. And you get negative x to the fifth plus positive 5x to the third minus 4x. It changes all these signs. And so comparing these two, yes, f of negative x is equal to negative f of x, and that is the odd test. So they are equal. It passes the odd test. So what kind of symmetry is it? It actually has, this is an odd function. It has rotational symmetry about the origin. And you can actually, put your finger right here on your packet. You can like pin that down with your finger and then spin the paper around 180 degrees, and you'll be looking at the exact same graph. That's what we call an even function. It has rotationally symmetric about the origin symmetry. Let's think about the domain. Well, it looks like we can put any value we want in for x and get an output for y, so the domain is all real numbers. And the range is all real numbers. We can see if we were to make a table of all these points, the collection of all the x values would be all real numbers, and the collection of all the y values would also be all real numbers, considering the fact that these go to negative infinity and this goes up to positive infinity. It's continuous. You could draw the whole thing with one swoop of your pencil. You would not have to lift it up and put it somewhere else. There's no breaks in it in any way. And it is not one-to-one. You try and draw a horizontal line right through the middle, and it touches more than once. In this case, it touches, right, if you go right along the x-axis is a horizontal line, it touches 5 times. So that's just too many. It's not one-to-one. I wanted to say that for your audio check, I met my wife in what you would call players at SCH, and I was a senior and she was a junior, and we had a wonderful time. We both had prominent roles in the High School Musical, and it was a great time for us, and just that was the beginning of a relationship, and there's your audio check. If you want to talk to me about it, or just comment about how weird these audio checks are in class, then that's when I'll see you. Hey y'all, we're going to spend a hot minute on nSpire skills, so grab that calculator, and then when you come back, you can unpause the video and do what I'm doing here. And now that you've got your nSpire calculator in hand, let's rock and roll. So we're at the home screen, and we're going to go B, graph, and tab to get to the function editor. I'm going to type in a function like x raised to the third power, x cubed. Exiting the exponent, we've got minus 2x squared. Exiting the exponent, boom, we've got our graph. And that's a really fun looking cubic curve. We're going to the menu, analyze graph. We're going to find some extrema, and here they all are, minimum, maximum. Now it needs some things. You can see down here it's asking for the upper bound and the lower bound, upper bound, and you have to tell it. You can't just say the whole find the maximum. You have to say within a certain region, and a certain region is right there. Let's do that again. Analyze graph. Let's find a minimum in a certain region. It's asking for the lower bound, and then it's asking for the lower bound. Boom, and now it found its minimum. You can see and it even gives you the coordinate points. Tab, up, let's clear the whole thing, enter. And that's it.